Okay, so we're adding this glue. That's what's going to make particles sticky. But the next step is, or maybe the first step is, we have to do something to get these particles to touch each other. We have to get them to collide with each other so that they can attach. And these are some potential transport processes. And I'll go through slides for each of them. Each of these transport processes is an interplay between two forces. In each case, viscosity is trying to slow things down. And I realize that in our lives, we don't really experience viscosity very much. We're big enough that we have enough inertia and our muscles have enough strength that we don't really think about viscosity. Matter of fact, if you're swimming, the big experience that you have when you're swimming is not so much viscosity as it is the fact that the water has a lot of mass and you're having to you're having to change your kinetic energy into energy in the water. You're having to move the water, and that's what's robbing you of energy as you're swimming. But if you were thinking about like moving your finger slowly through very thick molasses or honey, then you could get this experience of viscosity where it just is trying to make you stop all the time. So viscosity is this force that's trying to make everything else stop. And then there are these 5 other forces that we have that could be used to get relative velocity between 2 particles that would make them collide. First one is differential sedimentation, where gravity is the one that we're playing with. Next one is turbulent mixing, where the fluid has and particles have inertia. The next one is viscous shear, where we're applying a shearing force to the fluid, and that's causing the fluid to deform. Next one is molecular diffusion, where the molecules in the water are shaking around because of their thermal energy, and that's causing things to move, but viscosity is trying to damp it out. And by the way, Albert Einstein derived the equation describing that, so that's kind of cool. And then there's molecular forces that act over very short distances that could pull 2 molecules close together. So those are the forces that are available to us, and we're going to figure out which one actually is playing the dominant role. In all cases, viscosity is trying to stop these forces from doing their thing. So here goes the first one. I filled up a tank with a whole bunch of particles, a whole bunch of clay particles, and the little red dots on them are coagulant nanoparticles. Okay, so I've got clay particles that are kind of brown, and I've got these coagulant nanoparticles stuck to them. And then, and you have to figure out how this is possibly happening, but this is happening. So somehow we've got some big flocks that are aggregates of many, many, many clay particles. And those big flocks have a high sedimentation velocity, and they are falling down through this suspension and colliding with particles on the way down and adding them to their mass. So they'd actually be growing in size as they slide down through there. Who wants to ask a question about this idea? Or do you want another illustration of when this would happen? I have to tell you the story. If you have 2 people going parachuting and you go up there, let's do it in a helicopter so we can discharge you while the helicopter's stationary. And let's say you are actually quite light, okay? And let's suppose that the instructor gave all of you the same size parachutes. I'm guessing they don't do this. I'm hoping that's not the case. But anyway, they gave you all the same parachutes, and you're told to jump, and you jump out. And then as you're jumping out the door, you look back into the helicopter and you realize that the next person coming is this 400-pound dude. And he jumps out. And you've been cautious and you've deployed your parachute quickly, and the other guy, the big guy, jumps out and deploys his parachute right away too. But what happens? Because he weighs several hundred pounds more than you do, he has a higher terminal velocity, and he comes and nails you, and I guess makes a flock. Okay, so you're settling at different velocities, differential sedimentation. That is a cool method of getting particles to collide. So that's one. Second one is inertia, and I couldn't think of any great ways to describe this. So here we are at Luna Park, and we are going around in one of these rides. I'm not a fan of parks, but I did do this at least once when I was a kid. And first of all, are there any collisions between people as you're spinning around in that centrifuge? Do you collide with other people in that centrifuge? Good, the answer is no. Otherwise it would be very, very awkward. You're all spinning together. And the point to take home is that within an eddy, you're all traveling together with this eddy, and so there are no collisions. So how would you get collisions? Well, I don't know. Like, if there were a whole bunch of these rotors going close together, and if occasionally there was a trapdoor that opened in the side of the wall and left one of you out, oh, that was awkward. Let's not do this in real life, okay? But you could have, if inertia was important so that particles sometimes went in a different line than the fluid and could interact with particles that are also going from a different line than the fluid in a different eddy, you could have two particles with their inertia that are colliding. Okay, so we did differential sedimentation, we did turbulent eddies and inertia causing particles to hit each other. And now we do number 3, where a fluid is deforming continuously. So we've got a fluid here, and I guess the bottom boundary is somehow attached on this fluid, and the top boundary is moving at velocity v. And you might have remembered the equation tau, the shear stress, is equal to viscosity times the u dy. You might remember that from fluid dynamics. It's one of the early equations that they teach. It's kind of like, this is Newton's law of viscosity for Newtonian fluids. In our case, if we have a velocity v at the top and a height h, it's just the shear stress is mu times v over h. And then we do this one more thing, and we take v divided by h, and we call that g. And look, v has units of meters per second, h has units of meters. So if you take meters per second and divide it by meters, you get per second. That's g. It has units of per second, and it's a measure of the rate of deformation of the fluid. How fast is the fluid deforming? And does anything exciting happen? Well, let's watch those 3 balls. There they go. Okay, and there were no collisions. That's really unfortunate. So we'll try again. Here's 2 more balls. Let's try those. So we're putting those in this velocity gradient. You see what's going to happen? The ball that is, let's go back. The ball that's higher up goes faster, right? Because there's a velocity gradient in this fluid. So if we do this again, and we put a faster ball further behind, we get a collision. And we get really excited about this, because look at that. There's this really simple mechanism where if we can take a fluid and we can deform it, particles that are in that fluid, even though those particles are exactly tracking the fluid, like their center is tracking what the fluid would have done at their center. And look at them, they can collide. That's pretty exciting. Okay, so that's fluid deformation. Here's the next one, molecular diffusion. This one you can look at all day, and maybe you can see that there's something moving there. If you look really close, you can see that those little grains of salt or whatever they are, I don't know what they were made of, are moving around a little bit in the water, and it's because of the molecules of water hitting the sides of those crystals. Molecular diffusion is not significant for particles that are more than a few micrometers in diameter, which means that clay is pretty much unaffected by molecular diffusion, and so it doesn't help us there. It is significant for molecules and nanoparticles, including viruses and also our coagulant nanoparticles. And then this last force is molecular forces. Now we're down at the scale of an atom or a molecule. The origin of this force is things that are beyond me, that are happening at the molecular level. The one that I kind of understand is electron clouds get pulled towards a more electronegative atom, and that results in a cloud of electrons that is more positive at one place and more negative at another. And so if you bring another, in this case, an HF molecule up, hydrogen fluoride molecule up, the positive side of that molecule will like to get close to the negative side of this molecule. That's the same mechanism that's happening in water, where in water, the oxygen grabs the electrons and leaves the hydrogens without electrons, leaves them positively charged. And that means that water molecules, if this, my hand is the oxygen and my thumb and fingertips are the hydrogen, another water molecule will like to come up and it will attach oxygen. The oxygen will get close to a hydrogen because the oxygen is negative, the hydrogen is positive. Molecular forces are real, they're a cool thing, but they only act over distances that are on the scale of the atoms, on the scale of maybe a nanometer or a couple nanometers. And so they don't have the ability to transport our clay particles that are separated by many thousands, many thousands of nanometers and get them to attach. So not relevant.